In this video, I'll be addressing the second situation from the hockey homework document. So this is Daniel's idea where he is pushing the two crates together, one in front of the other. First part of the question is to make a force diagram for this situation, and so that's where we're going to start. As we can see here, Daniel is pushing from the left side as I've shown it, and he's pushing on box A. Because of this, we already know we can draw on a force for his push on box A directed to the right. We'll call this push since that's where he's pushing. We also can see that he's not going to be touching box B directly, so he's not going to be able to directly exert any force on box B rather. We also do know that there will be some force acting on box B. We need to figure out where that's going to come from so we can look at what else could be in contact with box B. We see box A is in contact with box B, and so as Daniel pushes A, it seems reasonable that box A is going to push against box B. So we'll go ahead and draw a force on box B and label that box A to show that it comes from there. Thinking to our laws of motion, we know that Newton's third law tells us that for every action force there's an opposite but equal reaction force. So since box A is pushing on box B, that means that box B must be pushing back on box A. This should be equal in strength, but opposite direction, which means that we should expect to see some force going to the left on box A, and that will be exerted by box B. So we'll label it as such. That seems to be everything that we have in terms of things that are pushing on each other. But we also have to consider that friction may exist here. Since Daniel is pulling the box to the right, that means that friction force on each box will go to the left. And so we'll draw a friction force on here for each individual box. And so each box will have some friction force acting against it. With respect to the actual lengths of the arrows that we've drawn here, that's not going to be the main focus of part A because part A is just getting the general force diagram that we're then going to apply to parts B and C when we have a couple different situations that we have to deal with. So let's take a look at part B next. Part B is the portion of this situation where Daniel is speeding up from their resting point. And so we know that he's accelerating at 0.2 meters per second squared. Because the boxes are accelerating at this given rate, we can go back to our second law of motion to figure out what the net force must be on each of these boxes. To do that, we'll do that net force is equal to mass times acceleration. We know in this case that the mass of each box is given as 55 kilograms. And that the acceleration here of the actual box is going to be that 0.2 meters per second squared. And so when we multiply these out to get the new net force, it's going to be 11 newtons of net force acting on each of the boxes here. So you may ask why we are doing these individually, why we're using the mass of one crate versus the two crates, since we do have two crates here. The key behind that is that we are still looking at each of these crates individually. Because we're looking at them individually, we need to use the mass of each individual crate to figure out the net force acting on that crate. So when we label this on our force diagram as a net force, this is going to be the net force of the individual crate. So we can say that there's a net force of 11 newtons on crate A, and also a net force of 11 newtons on crate B. And so that will apply for this situation where we are now dealing with the acceleration. Moving on from there, we can start to think about what we know about the other forces acting on each of the boxes. We want to find the push force eventually. So the push force is the force on box A, but we may not be able to get there directly. So we'll just need to think about what we know along the way, and then what we can calculate based on interactions that we can show between the different forces. Based on the introductory information, we should know that the friction force will have a magnitude of 54 newtons. So this was found based on the previous parts of the question where we use the mass and the gravitational acceleration to find weight and then find frictional force from that. So each of the frictional forces here, each acting on a single crate, should have a magnitude of 54 newtons. Since those are going in the reverse direction, we know that they are going to be negative. So we'll go ahead and show each of those forces as negative by adding a negative sign onto each one. We then need to start looking for relationships between the forces that can help us solve for new information. Even though we're interested in one of the forces on box A, we're going to have to start in on box B here. The reason for that is that this situation gives us the opportunity to actually solve for one of the forces. We can see that we know the net force acting on box B, as well as all of the forces except one. Since there are only two forces acting on that box, knowing one of them means that we have only one unknown there. That's why we were able to solve for the remaining force there, whereas on crate A we have two things we don't know, and we wouldn't be able to solve for those without any other information. We can set up an equation based on the fact that net force is equal to the sum of all the individual forces. So in this case, our net force is 11 newtons. We know that one of the individual forces, the friction force, is negative 54 newtons. And the only remaining force is the box A force, so we'll leave that as an unknown. In order to solve from there, we're going to have to try to isolate the box A part using algebra, and we can do this by adding 54 newtons to both sides. When we do that, we will end up with 65 newtons equals the box A force. Now, at the moment, that might not seem like the most useful piece of information, just because it's on the diagram that we are not as interested in. However, if we look at how the different forces are related together, we can get some information that will be useful in finding the push force. The key here is that the box A force acting on box B and the box B force acting on box A are an action-reaction pair. We know this because action-reaction pairs fit the pattern that when one object exerts a force on another object, the other object exerts equal but opposite force on the original object. Because it fits that pattern, we now know that the box B force should have the same magnitude as the box A force, so it should be 65 newtons as well. But this one is going to be in the negative direction, so we'll give it a negative sign there. This is going to be helpful because now we have only one force that remains unknown on crate A, which is the push force we are interested in. In order to solve for that, we're going to set up a similar calculation to what we did on box B. We will say that our net force, which on crate A is still 11 newtons, is equal to the sum of all the forces acting on box A. This includes our negative 65 Newton force from box B, our negative 54 Newton force from friction, and the unknown push force. Combining stuff together, we'll see that now 11 newtons must be equal to what we have when we add together those negative values, which comes out to negative 119 newtons, plus our push force. We can then add 119 newtons to each side to isolate the push force like we would like to. And when we do so, we end up with the fact that 130 newtons is equal to that push force. This solves for what we were looking for. We were looking for how strong the push must be on the crate, and that is our push force. So 130 newtons would be the answer to part B. That takes us through the first couple parts of Daniel's situation, and I'll continue with parts C and D in the next video.